completed his doctoral degree from Drexel University, USA in the stream of environmental engineering in a year 2020. She has worked in a different environmental industry during a period of 2002 to 2009 in Maharashtra state and had a 5 years of teaching experience and 5 years in research areas. Dr. Leena Shivde is a member of Indian Waterworks Association, member of American Society of Civil Engineering, and got a certificate from IEMA, approved advanced course on environmental management system conducted by DNU. She also working as an internal auditor for a quality management system. During the time of research period, Dr. Leena Shivde ma'am assisted many projects on the stream of environmental engineering in USA. On behalf of our organizing department, I welcome you ma'am for the today keynote speech.
Thank you, Professor Suhas, for introducing me. I was a professor at Dayanand Sagar College also. So I'm kind of like, I'm connected to DSE, and it's my pleasure to be here. Thank you for having me today. So I'm going to start and share my screen. I hope everybody is able to hear me very clearly. Give me thumbs up. There is a thumbs up button here, right, in the reactions. So if you are able to hear me properly, just give me thumbs up. Perfect. Good. Thank you. I'm going to start sharing my screen, and I need another thumbs up when you see my screen. Okay. Perfect. Great. So yeah, today very related to probably what you have been hearing from past 4 days now, right? I'm going to talk about sustainability in civil engineering, and it's going to be an overview of infrastructure design and education. And as Professor Suhas introduced me as both, like, I have worked in the field of consulting engineering and education. So I'm going to present few case studies related to that. Some of them I have directly involved into, but some of them are from my lab and from the earlier researchers that I will be presenting. So I'll be talking today about, in general, what is sustainability and specific to sustainability in civil engineering. And I will go through a few case studies, as I said, and stormwater management, because that's my research area. And then another one, which is the traditional or the, like, the conventional pavement versus the pervious pavement. And then some of the education where I involved sustainability aspect into it, right? And how do we use this? I see a lot of students, and whenever I get this opportunity to talk with the students, I don't want to leave it. So I would like to keep this session as interactive as possible. So before I start talking, I just want to make sure that I'm not talking with the black screens, right? So even though you don't, make sure that you don't unmute yourself, but can you just give me 2 minutes, and can you quickly write into that chat box, what do you mean by sustainability? So I don't need a definition. When we say sustainable or sustainability, what comes to your mind? It could be a product, it could be a process, it could be a tool, approach, whatever comes to your mind. So I'm going to wait for 2 minutes and check in the chat box. Maybe Professor Suhas, if you can help me to check the chat box. Do we see people writing there? No?
Good morning, Nina.
Good morning,
Good
sir.
morning.
How are you?
Fine.
Yeah. Yeah, Rahul, we've no? Okay, probably I'm just talking with the blank screens then. All right.
Students
Let's
are
move
joining.
on.
Almost student strength is 81 now.
Mhm.
Please.
So what comes to our mind, like, the very definition of sustainable development is by this politician and really famous author. So it always comes to our mind that sustainable development is development that meets the needs of present without compromising the ability of future generations to meet their own needs, right? We have heard this uh, definition so many times, right? So how does it compare to the engineering definition, right? So engineering is definitely, we involve a lot of economics in it. If a solution is not economical, we won't call it as engineered solution, right? So what we consider in the engineering definition of sustainability is not just environmental, but also the economical and the social conditions, right? So the ASC definition of sustainability is a set of economic, environmental, and social conditions in which all society has the capacity and opportunity to maintain and improve its quality of life indefinitely and without degrading quality and quantity. Also, availability of economic, environmental, and social resources. So I am going to quickly show this. Are you able to see this
Living
video now?
systems have been around for a few billion years and will be around for many more. In the living world, there's no landfill. Instead, materials flow. One species' waste is another's food. Energy is provided by the sun. Things grow, then die, and nutrients return to the soil safely. And it works. Yet as humans, we've adopted a linear approach. We take, we make, and we dispose. A new phone comes out, so we ditch the old one. Our washing machine packs up, so we buy another. Each time we do this, we're eating into a finite supply of resources and often producing toxic waste. It simply can't work long term. So what can? If we accept that the living world's cyclical model works, can we change our way of thinking so that we too operate a circular economy? Let's start with the biological cycle. How can our waste build capital rather than reduce it? By rethinking and redesigning products and components and the packaging they come in, we can create safe and compostable materials that help grow more stuff. As they say in the movies, no resources have been lost in the making of this material. So what about the washing machines, mobile phones, fridges? We know they don't biodegrade. Here, we're talking about another sort of rethink, a way to cycle valuable metals, polymers, and alloys so they maintain their quality and continue to be useful beyond the shelf life of individual products. What if the goods of today became the resources of tomorrow? It makes commercial sense. Instead of the throw away and replace culture we've become used to, we'd adopt a return and renew one, where products and components are designed to be disassembled and regenerated. One solution maybe to rethink the way we view ownership. What if we never actually owned our technologies? We simply licensed them from the manufacturers. Now, let's put these two cycles together. Imagine if we could design products to come back to their makers, their technical materials being reused and their biological parts increasing agricultural value. And imagine that these products are made and transported using renewable energy. Here we have a model that builds prosperity long term. And the good news is there are already companies out there who are beginning to adopt this way of working. But the circular economy isn't about one manufacturer changing one product. It's about all the interconnecting companies that form our infrastructure and economy coming together. It's about energy. It's about rethinking the operating system itself. We have a fantastic opportunity to open new perspectives and new horizons. Instead of remaining trapped in the frustrations of the present, with creativity and innovation, we really can rethink and redesign our future.
So this is this slide is adopted from Stanford School. It's called D School or the Design School. And what we have is this engineering design, and what we really need to do to incorporate sustainability is we have to reevaluate our problem, right? Rethink and redesign our solutions. So right from like at each and every phase of our design to actual testing the prototype and to build our solution and even to dispose it or to just use it back into the process, right? So at each and every phase, we have to incorporate sustainability. Now, how do we do this? We talked about whatever we saw in that video. They were talking about the manufacturing, right? Different products. But how do we say the same thing about civil engineering, right? So we have various types of infrastructure. We have bridges, buildings, water treatment plants, wastewater treatment plants, roads, and just go on, right? And I think we are already working on reusing the ash into our cement. So we are kind of headed in that direction, specifically using our material in a sustainable way, right? So what I'm going to talk today in depth, how do we assess or how do we measure the sustainability, right? So there are various approaches that we can take to assess whether one product is more sustainable over other or one process is more sustainable over other, right? So the main approach is that there are many other approaches, but one approach is look into the life cycle sustainability, right? So we can look into the life cycle assessment, life cycle cost, as well as the social life cycle assessment. And we can combine these things and we can assess our process or we can assess our design based on one or more approaches. So I'm going to briefly talk about what is life cycle analysis or what is LCA. And LCA is defined as a tool to identify, and this is under ISO 14044, and it is defined as a tool to identify environmental burdens and evaluate the environmental consequences of a product or process or a service, right, over its life cycle from cradle to grave. Or we can also say cradle to cradle when we talk about like recycled materials, right? So the scope depends on where do you stop. If you just dispose a material, it will be called cradle to grave. And if you recycle a material, it will be called cradle to cradle. There is another term there, which is called cradle to gate. That means you are only looking into the acquiring raw material phase. Okay. So these are typical phases or stages of can everyone please mute their audio so that, yeah, thank you. So the scope, so life cycle assessment is divided into 4 different phases, right? First phase is defining our scope and goal. Then we looked into the life cycle inventory, and then we start like collecting data on that, right? And then comes the life cycle impact assessment and the interpretation of that data that we have collected. So let's just look at what exactly is the life cycle, right? So life cycle, this is just a generic diagram. It can be any type of material, right? So right from material extraction, it could be your material can come from a farm or it can come from a quarry, right? And so that's our material extraction phase. This then comes the material processing phase. And at each and every phase, you will have some inputs going in. Minimum is energy and water, right? And there will be some output coming out at each and every phase of this life cycle of a product, right? So material extraction, material processing, manufacturing, then use, and after use is the disposal phase, which is the waste management, right? So if you recycle, your material comes back and you can save the energy and water and land that is required for the material extraction, right? So this, yeah. And as I said, there are inputs at each and every stage or each and every phase of this life cycle. And there are outputs, which are like either atmospheric outputs, those are like atmospheric emissions or wastewater and other solid waste, right? Or co-products or other type of releases. So when we define like what exactly are we considering into our analysis, that's what we call it as a system boundary. Okay. So I am going to talk about these. So these were like few terms. They will come here in these case studies frequently. So I'm going to now start talking about the gray versus green infrastructure. So now let's see, whatever we talked so far is about the manufacturing. So how does this apply to civil engineering, right? So I have picked up a case study from New York City. And so a typical like city like Mumbai or even Bangalore, what we have is a combined sewer problem, right? So what it means is we combine our wastewater along with the surface runoff. When it rains, it just gets mixed up in the sewage and then goes to the treatment plant, and it like whatever is the capacity of that treatment plant, it gets treated, but some of it gets disposed directly. So that's what happens in New York City as well, because the city is pretty old, and that's how we used to manage our wastewater and surface runoff since 19th century, right? So, and we all know there are like the way we treated our um, surface runoff is as a nuisance. We just wanted it to be like, we wanted to get rid of it as soon as possible. So we ended up having flash floods because we are just like, rushing all the water into the nearby creek, and it's just going out from the street very rapidly. And we all have seen now the ecological impact of it. So what is the way out? What is the sustainable way? How can we rethink? Can we redesign this system? So what we can do is add the green infrastructure. So what we do there is we add plants. Where do we add plants? We just can take some part of street where, say, traffic island, right? We really just need some space. So we are going to just excavate there and add plants there. And this is how New York City and many other cities in United States and in all over the world, even in Bangalore, we have seen such. I remember it from fourth block. I think they have added these BMPs, or best management practices. We also call it as LIDs, which are like low impact development, and these are also called as green infrastructures. So, um, so New York City have added a ton of them into the watershed. So this is one particular watershed, which is Bronx River watershed in New York City. And I am only considering 2 combined sewer outflows here. Now, why did we pick these particular points? Is these are like the lowest one, and we can actually measure how much was the outflow and how many times did it overflow, right? So you can see it here on the map that HP07 and HP09, this is where the combined sewer actually overflows into the Bronx River. And this line here is the Bronx River. So one more thing we have to define is a functional unit. So what we are comparing here is, one is the gray infrastructure, which is the pipe that we have been doing from 18th, 19th century now, right? So we are trying to compare that to a green infrastructure. And what really is common there is this watershed that drains into the either into that sewer or into the green infrastructure, right? So the area that I'm considering is 784 hectares of area. And the service that any one of the 3 scenarios I'll be discussing on the next slide is like, is the purpose of it is to reduce combined sewer overflow, right, from this particular watershed. So I'm going to use the life cycle assessment to compare 3 different scenarios. First scenario is the green strategy. Manage 1/3 of the runoff from this watershed using different types of green infrastructure. So these are the 27.12 hectares of porous pavements. And we have like many bio-retention and pump out facilities. There are curbside infiltration planters and backyard rain gardens and subgrade systems, right? So using this as well as porous pavements. So these all various green infrastructure strategies are used in New York City, and particularly in that watershed. And the design runoff is like 2.5 centimeters on this drainage area. So you can convert that to volume, and whatever comes, that should be captured by these green infrastructures, right? And the green infrastructure area in this watershed is 5%. So then second scenario is the gray strategy, where you just add detention tank, right? And the third scenario is to add, take all that, like, the typical one, treat and then discharge. And here in this case, you might have extra overflows because you're not detaining it, right? As soon as it exceeds the capacity of treatment plant, it's going to just mix it in the river, right, along with the sewage. Okay. So this picture described, this is our scenario do nothing case, which is like, don't add any additional pipes, don't add any retention or detention tanks, just use what you have, right? So that's our control scenario. And our first scenario is adding another pipe. Okay. Then scenario 2 is we are going to add a detention tank. And scenario 3, our scenario 1 is our green infrastructure, right? And scenario 2 is the gray, which is adding a tank. And scenario 3 is a tank along with the treatment. Okay. And the methods used here are life cycle inventory analysis. And that was, and I'm going to explain those results in a bit. And estimation of energy variation at the wastewater treatment plant in scenario 1 and 2, and estimation of carbon sequestration and carbon dioxide reduction due to shading and induced energy saving in the buildings brought about by the tree in scenario 1. And in the gray, we don't have that, right? So life cycle impact assessment and computation of energy and greenhouse gas as life cycle impact, right? We have to decide what are the impacts that we care about, right? So this is where the cradle to green infrastructure, like that's what our scope is. And we are like considering the global warming potential here. So we are converting everything into equivalent of carbon dioxide. And so the figure here shows like whatever goes into manufacturing of that pipe or manufacturing of that, in case of green infrastructure, if you just divide it into each and every like small component. So if you just imagine any green infrastructure, it will have a soil layer, it will have a stone layer, then it has plants, and you obviously you have to, it's in New York City, so you have to get the plants from some nursery which is outside of New York. Also, you have to acquire all the material from somewhere, so you have to transport it. So you can see it here that there are like n number of things. You need some HDPE pipes, then you need some type of geosynthetic material, so all the geotextile material. Then you need mulch. You also need some like waste management remediation services, then electricity, iron, transportation, cement manufacturing, and concrete. So you can just imagine like, like you can go all the way back, but where do you want to restrict your scope? That you have to decide, right? So when we compared these three scenarios, what we realized was obviously scenario 1, which is the adding green infrastructure, is the really best scenario, where your combined sewer outflow is reduced, but at the same time, you have also reduced the carbon footprint, right? So the municipalities can decide if they want to go for gray or green. Obviously, both have cost implications, but if they have same cost implications, uh, then obviously the green infrastructure gives you benefit of having better carbon footprint, right? Now, let's see another case study, which is the conventional street versus uh, or a conventional parking lot versus permeable pavement, right? And the approaches used here are, so I'm going to use two different approaches. One is I'm going to talk about the life cycle cost analysis with implementation rates, and then life cycle analysis. And specifically, we are going to consider the energy here. So stormwater runoff reduction was calculated using a LIDRA model here. It's low impact development rapid assessment model. And the annual estimates of runoff were considered, as well as the life cycle costs were considered in this model. These configurations you can just define. So this all happens in the planning stage. So you don't have any green infrastructure, but before you put anything, you want to make that decision which type of approach you want to adopt for your city, right? So that's why these are all different configuration or different scenarios that you will be running before you take a decision in which type of technology you want to invest in. So then this LIDRA, uses stochastic model where the precipitation is, ensemble, and then from the non-parametrically, from historical data, using Markov chain and bootstrapping methods, we have generated the future projection for several years. And then we added the LID scenarios there and various adaptation rates, and multi-year simulations were carried out. And they were compared to the no LID scenario, right? The control scenario was no LID. And a typical, as I was explaining earlier, a typical lane, this is a traffic lane and this is a parking lane here. And this is the curb, and right into the parking lane or into the curb side, these LIDs are generally accommodated. And you can see the building line and the sidewalk, right? So the functional unit here was used as a neighborhood block. A specific set of LID strategies are to be constructed in the Bronx, and New York was this area was the pilot project, and this study area was 2.66 hectares. And it comprised of all lots included there, and the right-of-way surfaces was runoff flows to a single point at the downstream end of the street. Also, this particular watershed was again selected because this was towards the end of the watershed. So you could actually monitor the outflows. And water pollution control facility operation, that obviously, the wastewater treatment plant would consume, will consume energy to treat the water. So New York energy generation is 17% of the New York's energy comes from coal, 13% comes from petroleum, 25% comes from natural gas, and 25% comes from nuclear. whereas 13% of the energy comes from hydroelectric. A life cycle non-renewable energy inputs are 4.3 megajoule per meter cube, and the greenhouse gas emissions were 260 grams of carbon dioxide, equivalent carbon dioxide per meter cube. And this was a typical system boundary that was considered, right? So when it rains or after the precipitation, your runoff will be either on the street trees or it will be infiltrated into the permeable pavement, right? And both will have some energy implications and greenhouse gas implications. And the stormwater collection system as well as the wastewater collection system. So, and then it will go to the combined collection and the treatment service, which is the wastewater treatment plant. And there again, we will have some energy inputs and greenhouse gas emissions, right, associated with it. So the way we calculated, we consider again the entire life cycle for both, right? So this is the conventional street, and this is the with LID, right? And where like we consider the incremental energy and GHG, right? So Dr. Spatari, and this was done by Dr. Ziwen Yu. So we have considered like the LID construction materials and perforated pipes. Again, you can see here that each and every single thing that was involved was considered, and the energy required to manufacture and to operate that facility. And again, even for the disposal of it was considered, and considering all that, these numbers came from there. So what we can see is there is a ton of saving when we use the permeable pavement and the street trees, rather than just using the conventional street, right? So whatever information we see here, and when we consider, as I said, like earlier, that in this project, they have considered the economical benefits as well, right? So you can see the payback period for energy is 70 to 100 years. And for greenhouse gas, it's 130 to 180 years, right? So it's not like very lucrative, right? So we have to really understand the scope and goal of your LCA. What was the purpose of it? If you just look at the cost benefits, then obviously, you would like, if your payback period is 100 years, then why would you invest in that, right? But again, these results are very, very region specific. On the earlier slide, you have seen here that, in the New York City, the energy generation is done by like, these 4 or 5 different ways. But instead of that, if you consider Bangalore or any other city in India, the energy generation might not be like we don't use much of coal now. We have mostly hydroelectric and other sources, right? So the energy generation and the saving would be different than what we see here. So what conclusion from this study, I would say, is we should consider the ecological benefits as well, right? And the ecological benefits include the hydrological improvement in infiltration and water retention, as well as the evapotranspiration, and the carbon storage in case of plants and trees, like, the LIDs that uses plants. So, and this particular case study involved only one type of LID strategy, which was permeable pavement and the tree trenches. But the LID strategies will vary with different types of municipalities, right? So, and it is very specific to your water infrastructure. So such case studies involving cost as well as the decision makers should decide based, not just based on the cost, but also based on the carbon footprint or the the other trade-offs that they have to do. So municipalities can quantify and weigh the energy and greenhouse gas trade-offs and traditional versus green infrastructure to ensure that our resources that we have, they are limited resources, right? And we should consider the environmental, social, and economical benefits of it. So I have, last but not least, how do we, like we said, okay, I just talked about two different type of infrastructure projects here. How do we incorporate this into sustainability, right? So if you look at the ASC recent, like last year's journal, they said that we should train our civil engineers as sustainability leaders. And how can we do that? So that's what I am going to talk about. And this is my last case study. So this is something that I did in my course, right? So this course is undergraduate introduction to engineering course, and Professor Mary Roth, who is the professor and department head at Lafayette College. She has developed this course, and three professors, so me, then Professor Roth and Professor McGuire. So three of us taught this life cycle assessment module to three different sections, rather 6 different sections. And our course objectives were students will learn about sustainability. Why do we care about sustainability? Why do companies care about sustainability? These days, if you see many of the companies such as Dove, they all are investing into sustainability. They all have a sustainability manager. So why do companies care about it, right? Then life cycle thinking in general, and then how do we carry out life cycle assessment, and how we promote it as a measure of sustainability, right? And also the student projects, they help institute become more sustainable by making more sustainable choices, right? I'll talk about that in a minute. So the methods that we use, we start with empathy. We have on campus, we have a farmer who is we grow some crops here locally. And we also have a sustainability office at Lafayette. So the sustainability office makes sure that the college store keeps all sustainable material. And so the students start with empathy. They try and understand. So the professors give the projects, but also the sustainability office many times come forward and they want to carry out some of these studies. So we use those studies as student project. So the sustainability office is the actual client, and the students try and meet sustainability officers, and they try and understand what are the requirements and what products they are considering. And then the students conduct a life cycle assessment project. The method that we use here, we primarily use mainly the secondary data. We use collect data from the literature, just the way I showed some of that. That was mostly from literature. And then on that data, now collected data, we carry out different estimates, and the students complete entire streamline life cycle inventory analysis. We do not go into the assessment part, we restrict them to the life cycle inventory phase. And they interpret the data and they, come up with the conclusions which product is better over the other. Some of the projects that our students have done are blackboard versus whiteboards, chalks versus markers, recycled aluminum chairs versus recycled plastic chairs. Then disposable pen versus refillable pencils. Now you might find this funny, but since I am in US for last 10 years, and since I moved from India, I didn't see the refillable pens here. Most of the pens, they are like disposable ones. You just use it one time and just throw them away. I haven't seen the refills. So that's why we have considered that disposable pens versus refillable pencils. Pencils on the other side, you get the, the lid to refill it. Then mulches, different types of mulches. Wood chips versus straw cover versus the plastic sheet, so that your plants are safe from weed. I also developed another another course, and this is a typical like a strength of material course where you actually just solve some problems, right? But I added few things there so that student, they still learn about sustainable material and what are the implications of that, like the engineering properties, right? So can we engineer more sustainable material? When we do that, like these were the course objectives, just specific to this project, right? Entirely, like we know whatever typically we teach in strength of material that I had, but in addition to that, I added this project just to make them understand or give them opportunity to understand the sustainability aspect. So what are the implications of material on strength of structure? What are the cost implications? As well as can we play with geometrical properties to get higher strength, right? And these are a few pictures of the the girders that my students made. So we used popsicle sticks, and they they developed these different types of girders, and then we just continued. So whatever problems, instead of using the typical cross sections like eye cross section that we have in the textbook, so instead of that, we just replace the cross section with whatever they came up with here. So you can see, the shear adding that weight actually failed that girder, in shear. So they could visualize it. So my strength of material purpose was also served. They could just visually see everything happening there. But as well as I cannot test steel beams, especially here, right? If we were, if it wasn't a COVID scenario, we would be in the lab and I could just, take them to the materials lab and show them everything. But that wasn't the case. So this was one of the idea that I use that involves sustainability. Okay, so what they essentially did, you saw the pictures of that, but what exactly is that is they built girder out of popsicle sticks, and they use different combinations of cross-laminated and glue lam is the glue laminated timber. And we encourage and mentor students to participate in timber design competitions. And we test the material, we encourage them to research on that and estimate what are the implications of using sustainable material, right? So way forward, we have to incorporate sustainability into education, into our personal and professional commitments, as well as institution and organizational initiatives, right? We should reduce our carbon footprint, water footprint, and ecological footprint. And this is something Lafayette does. We use the regenerative ecosystems, zero waste, and the circular economy, food loop, and carbon neutrality, social justice. Just to show, these are like, on the campus, these are like everywhere you will find the recycling spots. And it's not just for the campus, but even the community around can come and, recycle here as well. And thank you for having me. If you have any question, I won't be waiting till end of the session, so because it's already 12:30 here.
Thank you, ma'am.
We can
So I
open
request
for
participants
questions.
any query or any comments. You can unmute yourself.
So I know when I was in DSE, I heard that like we had a, I think, was there a digester, Dr. Ramraju? I think we used to generate,
Tell me.
sir, we had a digester, right?
Yeah,
Do we still have it?
still we have.
Yeah.
We have in the library. I mean, in your environment engineering lab.
Oh,
We
no,
have-
no. I thought we had like as a sustainability, just initiative from DSE. I thought we, like one of the earlier professor had developed a, a digester plant.
We have one digester where one of the MSc engineering research student from chemical engineering department, we used to carry out these experiments in our environment engineering lab, which was funded by VTU, where I was the principal investigator for that. He carried out the experiments in our environment engineering laboratory only, using the same equipments and all.
Okay. No, I mean, I thought the composting plant, that type of digester. Yeah. Any? I can take any questions if anyone have.
Participants, if there are any queries, you can unmute yourself.
I think next session is going to start at 11:45. It is wrongly framed when you are framing that. That is what I requested my co-investigator, the coordinators to look into what exactly the program they have planned. Anyway, no problem at all. Now let us break. Let us reassemble at 11:45. I request all the students and other participants to come back and report back in the same link by 11:45. We thank, first of all, Dr. Lina Shevde for making free that was this time. That I think it's the midnight there. Lina, what is the time there?
It's 12:30.
12:30 night.
Yeah.
Okay, very sorry, because even yesterday, day before yesterday, same thing happened with Dr. JP Singh. We are very sorry because about the timings and all. You can, I thank you a lot. Next, passing to Suhas, please. Suhas, you can continue further. And
Yes, sir. Thank you, ma'am, for the wonderful session and sharing your experience and your work.
Sure. Thank you so much. Thanks. All right. I'm
So-
going to switch
Okay.
off.
okay, thank you, Lina. Good night.
Thanks.
Thank you, ma'am.
That is what it is. Okay, thank you. Good night.
Yeah.
So now we will take one short break, and the session is resumed at 11:30. That is technical session 1. We will meet at 11:30. Thank you all.